Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Jonathan Tan, who is Professor of Astronomy at Chalmers University of Technology at Gothenburg, Sweden, and at the Department of Astronomy at the University of Virginia. He coordinates the activities of the Chalmers and Virginia initiatives on cosmic origins, which are interdisciplinary initiatives in the field of origin science. Welcome, Jonathan.
Thank you, Gill. Glad to be here.
Yeah, thanks for doing this. I want to start with one of your older papers from 2000, Star Formation Rates in Disk Galaxies and Circumnuclear Starbursts from Cloud Collisions. You say in this paper, we invoke star formation triggered by cloud collisions to explain global star formation rates of disk galaxies and circumnuclear starbursts. Previous theories based on the growth rate of gravitational perturbations ignore the dynamically important presence of magnetic fields. So you do a lot of work in star formation, especially in massive star formation and supermassive black holes, which we'll talk about as we go forward. But this is sort of talking about star formation in general, right, this paper?
That's right, Gill. So star formation is a fundamental process in the universe. It's happening in our galaxy today. Every year, there's a few new stars appearing, and that's been going on for billions of years. That's gradually how galaxies evolve, turning their interstellar gas into stars. So yes, this paper that you mentioned then tries to understand the rate at which they are forming stars from their gas.
Okay. And one of the important, I guess this is still sort of evolving, and that is the presence of magnetic fields in star formation process, right? Could you talk a bit about that?
Absolutely. So one thing that we do know when we observe how fast stars are forming in galaxies is it's actually a very inefficient process. If you think about a natural timescale for how quickly stars should form in our Milky Way, it should be really forming 1,000 stars per year, but in fact is really only forming maybe 1 or 2 or 3 stars per year. So it's very inefficient. And there are a number of ideas about what processes could be basically slowing it down, resisting gravity. And magnetic fields is one process, turbulence is another process, feedback from already formed stars exploding as supernovae or their winds or radiation is another set of processes. And so these are, I say there's no real consensus yet on understanding what is setting the rate of star formation in galaxies. It's some combination perhaps of all of these things.
Yeah, so it's inefficient, as you say, because the number of stars formed in a very active area appears to be quite small. So I don't know a lot about this, Jonathan. So this is sort of a very intricate balance, right? As mass
gets gravitationally pulled in. The mass has to go in at some sort of specific rate for this to work, right?
Exactly. So, of course, we have gravity compressing gas, and it's then the question is, what are the important things that are pushing back and resisting that collapse? So, as we mentioned, magnetic fields, some kind of pressure force from thermal pressure in the gas, some kind of ram pressure force from flows, which could be turbulent flows, or they could be winds from stars that are forming. So it's this competition, which means that it's occurring over a very wide range of scales in our galaxy, and because of that, it's quite a complex process where things can operate from the scale of a star, which is about a light second across, all the way to thousands of light years. And across this very wide range of scales, we need to basically follow the evolution of the material as it's collapsing and trying to form stars. And one other thing we notice is that stars tend to form in clusters. So they form in bursts. You can think of them like fireworks going off. So it's a very concentrated process. So when it does happen, it appears to happen quite well and quite efficiently in bursts. Most of the gas in our galaxy is actually not forming stars and is basically inert to star formation and is being stopped by something.
Right. Yeah. So you have another paper from 2006, Equilibrium Star Cluster Formation. You say we argue that rich star clusters take at least several local dynamical times to form, and so are quasi-equilibrium structures during their assembly. Local dynamical times, what does that mean?
Right. So a local dynamical time of a system is basically the time scale on which information could be transmitted across it. And information in this sense is being transmitted by pressure waves or waves due to fluctuating magnetic fields known as Alfvén waves. So they travel at a certain signal across the cloud. Basically, if I was to heat up one side of the cloud and raise its temperature and pressure, how soon would that pressure wave travel across the cloud? That's a crossing time or a dynamical time. And in a cloud which is bound by gravity, there's another time which is called the freefall time, which is basically how long it would take to collapse all to the center and become very dense. That's actually very similar to this sound crossing time for these kinds of clouds. And for a typical region that's in a molecular cloud that's going to form a star cluster, the typical timescales can be about 1 million years.
Wow, yeah. And so, as you mentioned, there's a sort of a nursery effect, the star cluster formation. So if certain conditions are right, stars seem to form quite rapidly, the number of stars, and then if they're not right, we get very few. Is that the idea?
Yeah, so this actually brings back to the first paper you mentioned. So in that paper, the mechanism we were proposing that could be very important is actually compression of gas in cloud-cloud collisions. So the picture we have in mind is that the galaxy has these molecular clouds orbiting around, and because some clouds are on inner orbits compared to others, they basically catch up with another cloud and bang into it. And that compresses a part of the cloud to high densities, basically makes it gravitationally unstable, which then creates this burst of star formation in a little cluster there. So that was the idea we proposed in 2000. But then that cluster, that when it's forming, it will have quite a short dynamical time scale when it's been compressed to high density, so about 1 million years or maybe even 100,000 years. And then this idea of equilibrium cluster formation is once we have this gas compressed locally inside this cloud, is it ever reaching a state of near equilibrium where the rate of star formation is actually being regulated by maybe feedback processes from the stars that are forming, or magnetic fields or turbulence.
This collision of these gas clouds, they're similar to sort of the galaxy collisions, but in this case, essentially you have a very very violent process, right? Because it's dense. These two things that are colliding.
Right. These objects, which are clouds orbiting in our galaxy on approximately circular orbits around the galaxy, like the sun, that they're orbiting around maybe at 200 kilometers per second. It takes maybe 100 million years or a couple hundred million years to orbit around once. What we showed in this work is that perhaps every 10 million years or every 20 million years, they are going to suffer collisions with other clouds. And in that process, then the relative speeds may be perhaps 10 kilometers a second between the clouds. But that's still faster than the sound speed in the clouds, and that's enough to create a shock wave, which then compresses the gas and can then, we think, trigger star cluster formation. And there's been cases in sort of case-by-case sense where astronomers have looked at particular clusters and concluded that this process is happening to some extent. What is less clear is how universal it is, if most stars are triggered in this way or not.
Yeah, so the existence of this gas clouds, Jonathan, do we have sort of an idea of how they're evolved? So the reason they exist, the reason a gas cloud exists is that it didn't have an opportunity to collide with something else.
That's a great question. So in our galaxy, there is gas between the stars, the interstellar medium. I like to think of the galaxy as an ecosystem, as a balance of flows of matter and energy. So we have some matter is flowing from gas into stars. Some new material is falling into the galaxy, replenishing that gas. Some gas is being returned to the interstellar medium after the end of stellar evolution. So there's flows of material in the galaxy and flows of energy. And then within the interstellar medium, the gas is organized into different types of phases, we say, of the gas. So some can be cold and hot, and the cold ones have a chance to cool and contract under gravity and form dense clouds. So there's a cycle, and it's quite unclear how long various, if you're a given hydrogen atom or molecule, how long you spend in each phase. We can measure how much mass is in the different molecular clouds or atomic clouds, and within the orbit of the sun, for example, there's about an equal balance. So just from a statistical argument, gas must spend half its time in the atomic phase compared to the molecular phase, roughly. But then how quickly it cycles back and forth between the phases depends on what's exactly happening. So for example, one extreme scenario is all the molecular gas forms stars and then would have to be replenished by new material returned from the stars, perhaps. Or it could be, the molecular gas could be dissociated by radiation fields, turned to atomic, and then the atomic gas just circulates back into molecular clouds without star formation being involved. So you see this range of possibilities. These flows and these cycles need to be understood, and because these things are happening over millions of years, we get a snapshot today with our telescopes. In any given region, things may vary. So one really has to take an average across the whole galaxy to get a full picture of the demographics, just like somebody doing polling would have to measure a whole range of people of different ages to get a census of the whole population.
Yeah, so material is being recycled. So is it correct to think about this, Jonathan, that a galaxy is sort of sitting on top of a gas cloud, and there's material going into it, there's material coming out of it. So it's sort of surrounded by these gas clouds, each galaxy, including our Milky Way.
Well, the real backbone, we think, of the galaxies is the dark matter halos. So we haven't talked about dark matter yet, but we think most of the mass in the universe is in the form of this dark matter. We're not quite sure what it is, but this dark matter then has actually condensed under gravity and formed these structures into which gas has fallen and cooled. And as it cools, then it settles down into these thin disks. It has some angular momentum, and that angular momentum is conserved, and that's why most of these galaxies, we see them as disk galaxies, because the gas cooled and settled down. Originally, they were much more gas rich, but then over time, this gas has turned into stars. And so in our Milky Way, most of that mass now is in the form of stars, and maybe just 10% is left in gas.
But 10% is left. So you have another paper in 2014, massive star formation. I want to get sort of a quick idea of the demographics of stars, Jonathan. So what is a massive star in terms of solar masses?
Right. So when we refer to massive stars in the community, in the research literature, we're typically dividing things that are more massive than 8 times the mass of the sun. And there's a good reason for that. That they end their lives in a very different way than lower mass stars, less than 8 times the mass of the sun. So these massive stars that are more than 8, they build up an iron core in their nucleus over their lifetimes, which eventually will grow to a mass which can no longer be supported by its internal pressure, and that collapses in a very violent event, leading to a supernova explosion, a core collapse supernova. At lower masses, you never build up enough mass in this core to eventually collapse, and you have a very different end product of stellar evolution, a more gentle evolution to planetary nebulae, leaving behind a white dwarf. So that's the conventional distinction. Now, we know there's stars of a very wide range of masses. Yeah. So we talk about, in reference to the mass of our sun, 1 solar mass. So the most massive stars that are known in the universe that we've seen, astronomers have seen, are about up to maybe 300 times the mass of the sun. Are some few claimed examples in nearby galaxies, the Magellanic Clouds. But most stars are not massive. So you probably have 1 massive star for every perhaps 100 or 1,000 low mass stars. So most stars are like the sun, or actually the average is about half the mass of the sun. And then it continues down at the other direction. So you can have objects down to less than 1/10 of the mass of the sun. And at that point, they're no longer hot enough to undergo fusion of hydrogen in their centers, and so in some sense are not really stars in powered by nuclear fusion. And below that, we call them brown dwarfs. So that's below about 8% of the mass of the sun. And there could even be free-floating planets down there as well, potentially could have formed in the same result of the gravitational collapse process of star formation.
Yeah, so stars in this context are things that is undergoing nuclear fusion. It's producing energy, it's producing light, we can see them. That is what we call stars, but there are objects out there that is really, really massive, lot more massive than stars, as we call it, right?
Well, perhaps you're referring to supermassive
black holes, and even things like neutron stars. So I'm going back to the 300 solar mass as sort of a big as a massive star, but that is just the star, right? It's not really the objects that we have in the universe that's substantially bigger and more massive.
Well, in terms of these objects which form stars, as I say, that's probably the most massive claimed example, and there are very few such examples. So we've not seen any direct evidence for things that are 1,000 times the mass of the sun or 10,000 times the mass of the sun as stars. There are, as you go higher up in mass, there are objects. I mean, you can come to molecular clouds that might have 1,000,000 times the mass of the sun, but typically they'll fragment into many stars. Within the nuclei of galaxies, there are these supermassive black holes. So our Milky Way has an object 4,000,000 times the mass of the sun. In some of the giant elliptical galaxies, they can be several billion times the mass of the sun. So these objects are at quite a different scale away from stars. Then at the end, but for normal stars, and including massive stars up to a few hundred solar masses, they will evolve their lives and typically lose a lot of mass, especially the massive stars, during their lives. And they can then leave behind neutron stars, is a common outcome of core collapse supernovae. But most neutron stars are only a few solar masses at most. And then beyond that, we think, in fact, that they would actually have to be black holes. And so black holes are thought to form from some core collapse supernova explosions. And so that 300 solar mass star is probably on its way to eventually collapsing and could well form a black hole that might have perhaps 100 times the mass of the sun, depending how much mass has been lost by the star during its life. And recently, in the last several years, from gravitational wave observations, we now know that there are some populations of binary black holes with several tens or even close to 100 times the mass of the sun. But we think these probably formed as the end product of perhaps some of the most massive stars that are, in some sense, part of the normal population we're seeing forming in our galaxy and other galaxies.
Right, yeah. So let's talk about black holes. So you have a recent paper, The Formation of Supermassive Black Holes from Population 3.1 Seeds, Cosmic Formation Histories and Clustering Properties. So black holes, as you mentioned, at the end of the life of a star, there is a supernova, and that could result in a variety of objects. And one of them could be a black hole. But the black holes themselves, there is a huge range in terms of their masses, right?
That's right. So these supermassive black holes that we now know are in the centers of galaxies, it is very unclear where they come from. So as we've seen, that they're at a very different scale than the normal stars we see around us. So even this most massive star that I said is about 300 solar masses, there's no way it's going to make a supermassive object. Just not enough mass there. So it's a big open question. I think one of the most important open questions now is in astrophysics is where these supermassive black holes come from. You see that they're the centers of most large galaxies, and they can have a dramatic effect on the evolution of galaxies because they release a lot of energy as quasars and active galactic nuclei. So yes, it's a big question where they come from. What we've proposed in this recent paper you mentioned is that the very first stars to form in the universe could have been a very interesting place. So the traditional view for these very first stars is that they were massive, but perhaps only 100 or a few hundred times the mass of the sun. So nothing completely out of the ordinary. What we're proposing in this paper, building on work that has been developed by a couple of groups around the world, is that maybe these very first stars were actually quite different, radically different, and underwent a very different stellar evolution because they are forming in the centers of dark matter halos. Because they were the very first objects to form, their locations are predicted to be at the very center of the dark matter halo. So the galaxy is just starting to form, and at the very center, the dark matter is at the highest density. Now, we don't know what the dark matter is, but probably the most popular idea is it's some kind of new particle that hasn't yet been found by particle physicists, but it is a weakly interacting massive particle. And such particles may well, very, very occasionally, annihilate with each other. They're their own antiparticle and release energy. So basically, when matter and antimatter collide, energy is released. And that could be a power source different from nuclear fusion, which is powering these very first stars. So what we've discussed in this paper is scenarios in which this dark matter annihilation power source allows the gas in these first halos to basically collapse down and reach all to the center of the halo and allow a supermassive star to form. So this would be a star now that would be perhaps 100,000 times the mass of the sun. That's the conventional scale. We use the phrase supermassive. And then this is an object which would live perhaps a few million years, but eventually would also explode or collapse in a supernova, and leave behind then now a supermassive seed black hole of about 100,000 solar masses. And this is an idea then that's a little controversial, I would say, but it's interesting because astronomers now are finding evidence for supermassive black holes very early in the universe, just a few 100 million years after the Big Bang. And so you really do need a mechanism that can make these black holes very early and make them massive enough and make enough of them. You see, we're trying to explain all of the supermassive black holes by this mechanism because they are a very different scale from the normal stars. We want to invoke quite a different mechanism from conventional star formation physics. And this could be one way to do it, using these dark matter annihilation-powered first stars.
Yeah, so that makes it both complicated and interesting. So since we don't really know what dark matter really is yet, and if we are hypothesizing dark matter halos had a significant role to play in early massive stars and black holes, that it becomes it becomes quite complicated, right?
Well, exactly. So that in this sense, the outcome of the star formation process does depend on the nature of dark matter. So it does require dark matter to have clustered on small scales and be captured into these stars. So we actually care about some of the particular properties of the particle nature of dark matter for this scenario to work. But that's, of course, interesting that the model makes predictions then, which can eventually be compared to experiments in particle experiments that are testing these properties.
Yeah. Do you think this will have some beneficial effect for us to actually determine what the dark matter might be?
So what we need for this mechanism to work is that the dark matter is cold, but there's a lot of evidence for that generally in trying to understand cosmic structure formation. So that's not a controversial topic. That's within the mainstream, that the dark matter is a relatively massive particle that is able to cluster and form these halos, which are then the seeds of galaxies. What we do require is that the dark matter can be captured into a star, and at a sufficient rate that there'll be enough of this annihilation heating to allow it to grow up to this 100,000 solar masses. And so that does require certain rates of interaction of this weakly interacting particle with, say, hydrogen nuclei to cause the dark matter to scatter and lose enough energy to settle and sink into the star. And it's only at the very center then where the densities would rise high enough that this annihilation strength would be strong enough to produce enough power.
So what is the driving force toward that idea, Jonathan? The annihilation that requires an antimatter particle. Do we have some evidence or some idea why anti dark matter particle would do this?
So again, we don't know what the dark matter is. We don't really know if it's in this family of the WIMPs, the weakly interacting massive particles. There are other ideas out there, but one very probably the most popular idea is that dark matter is a weakly interacting massive particle, perhaps what's known as the lightest supersymmetric particle from the ideas of supersymmetry, where, for example, electrons have their supersymmetric partner, and the photon, all the bosons, the photons also have a supersymmetric partner. So in that theory, which is again fairly it's conjectured, but it's certainly not proven, but it has been perhaps a framework in which particle physicists are setting out their explorations. There is a lightest supersymmetric particle not yet discovered, and it would be the stable particle, and that is a good dark matter candidate. So this particle then is behaving in a very strange way. It interacts gravitationally, but doesn't interact very strongly at all with the electromagnetic forces, so with photons, or basically with matter in any strong way. That's why it's been so difficult to detect. But only occasionally it will scatter, or with normal matter, and then lose energy, and in that process it can settle to the center. Perhaps an analogy is a particle called the neutrino, which are well known and well studied. They interact very weakly with normal matter as well. So they have a very weak cross section, and they're extremely well studied. I mean, they're produced in the sun, they're produced in supernovae. Astronomers have neutrino telescopes now to see these things, but they're only detecting one particle out of many billions and billions, or more, even more, because they interact so weakly. So something analogous we think may be happening for these WIMPs, these weakly interacting massive particles. It's just that they're not neutrinos; they're quite massive particles which can cluster together. And they're not traveling at high velocities like neutrinos are, close to the speed of light. They're traveling much more slowly. They can cluster into these dark matter halos. This is the proposal, but as no one has yet detected the dark matter, this is the problem. So there are huge amounts of effort going on around the world in experiments, underground and deep down in mines, to reduce the contamination and try and see these very weak signals from dark matter that would interact with the detector. There's predictions, if they exist, that in the dark matter halos around us today in the galaxies, there should be this annihilation process happening, which would produce gamma rays. And there are gamma ray telescopes in space, staring intently at these some nearby galaxies and placing constraints, placing limits on the rate of this annihilation because they haven't seen it yet. So all of these experiments are very interesting and really testing and constraining what this dark matter can be. Right now, the model we propose using this annihilation energy is consistent with all these latest constraints, but maybe in a few years from now, if they haven't found anything, we will have to revise our proposal.
Yeah, so if I understand this correctly, Jonathan, there is general consensus that the supermassive black holes that we find at the center of galaxies, maybe 1 million solar masses to 1 billion solar masses, require a different mechanism altogether for formation, right, than other mechanisms that have been talked about for smaller black holes or even intermediate-sized black holes. Is that right?
Yes, that's right. Because there appears to be this separation of mass scales, we don't see a lot of objects around 10,000 solar masses or 100,000 solar masses. And in the nuclei of galaxies, that's the mass scale where we start to see these supermassive black holes. So that argues maybe there's a different physical process leading to their formation. And there's a number of ideas out there. So one is the direct collapse model of black hole formation, which basically has a lot of gas flowing into a concentrated region very quickly, but also not able to fragment into a normal population of stars. That requires very special conditions. And astronomers and astrophysicists have been trying to simulate in their computers how often that would happen. And while they can create those conditions occasionally, perhaps enough to explain the observed black holes that are seen in the very early universe, they struggle to make enough of the black holes to explain all of the ones we see around us in the nuclei of all the massive galaxies. And so what has drawn me and my collaborators to this alternative view is that this is a mechanism which can quite naturally explain all of the supermassive black holes. It's just that we have to do it very early in these special conditions, and we are invoking new physics from this dark matter annihilation heating. It makes a very strong prediction that all of the black holes that are in the nuclei of galaxies eventually, they would already have been produced within maybe 300 or 400 million years after the Big Bang, basically before the galaxies formed. So we're predicting if you like, a quasar-dominated era in the very early universe in this theory. And it obviously makes then predictions for that, which perhaps new telescopes coming along soon will be able to test.
Yeah, I mean, there's a chicken and egg problem, right? Did the galaxies happen first or the black holes happen first? And yeah, if I understand this correctly, Jonathan, your idea is basically saying the black holes happened first and then galaxies organized around that. Is that right?
Yes, exactly. You have the idea exactly right. But I would say it's certainly by no means proven, and this is how science works. So we will aim to test both if when we have telescopes which can observe these very early times routinely, like the James Webb Space Telescope coming up. These will be things we can look for with such telescopes. I mean, there are a number of other predictions. This model actually predicts that the black holes are not very clustered, so that they're actually relatively spread out in the universe, and so actually would not be merging very often, so would not be producing gravitational waves very often. And so there are attempts to measure the gravitational wave signatures from such events with both pulsar timing arrays, the nanograv project, and then in the future, the space-based laser interferometer LISA mission will also be able to measure gravitational waves from merging black holes like these. And so we're actually predicting they're not going to see too many of these sources, occasionally some. And so that's again, another prediction. Yeah. We also aim to predict how clustered these black holes are locally today. So we can evolve in our computers, we can evolve these halos forward in time. They grow and form the galaxies. And what we're doing is populating certain special halos, dark matter halos, with black holes. And we then make predictions for where they should be today in the universe, which can be compared again to surveys of such black holes.
Yeah, they seem to be nicely distributed. Galaxies can form around them. What's the connection to the quasars? So those are objects we're looking back in time, maybe close to 1 billion years from the Big Bang, and that's right. So what's the connection there?
So quasars, I mean, that term comes from the 60s, the quasi-stellar objects. They were seen as point-like optical sources. Vast amounts of energy are being released. When they realized these quasars were actually across the universe, very far from us, and not just normal stars in our galaxy, then we realized that there must be a huge, enormous power source that's creating this enormous luminosity that makes them so bright, so far away. And the only plausible energy source is when matter gets very hot as it's falling towards a black hole. Then very hot matter radiates very strongly, releases a lot of energy in the form of light, and that's what's seen. So this matter swirling around a black hole is a very concentrated power source. And then the other piece of evidence that's very clear is that these quasars can change their brightness, so they can fluctuate on time scales of months and years. And it only makes sense if that's an object which is less than a light year across to change its brightness so quickly. And again, the only plausible power source then is this swirling material around a supermassive black hole, which is a very concentrated source.
So are we really saying that the quasars that we pick up are actually potentially the supermassive black holes, and the energy that we are seeing is from the mass falling into the black hole?
Right. To see a quasar, we need a supermassive black hole to be there. But we are only really going to be able to see these supermassive black holes if they happen to be feeding, if they happen to be gaining material in sort of falling into them at the moment. And many black holes around us today are certainly not very luminous. So the one in our own galaxy, we wouldn't notice it if we were on the other side of the universe, for example. So the question then is the so-called duty cycle. How often are the black holes feeding? And that is a little bit difficult to predict, because it requires following the evolution of the gas clouds in galaxies. Much as we mentioned at the beginning, these gas clouds can be orbiting around, and it's complicated, affected by turbulence, magnetic fields, star formation. So how well we can feed in this gas to the black hole is there's no settled or simple way to predict that.
The number of quasars we see, sort of the density of quasars, should be related to your hypothesis, right? So wouldn't you be able to predict if they were actually supermassive black holes, about 1 billion years from the Big Bang? Wouldn't you be able to predict how many you will find?
Exactly. So the theory we've proposed, it does have a what we call a free parameter. That there is some uncertainty, and that is basically how often do these seeds come into being, in which particular of these first stars. So the idea is that when this in a local region of the universe, you actually need quite special conditions. You need the star to be forming in the center of the dark matter halo, and we think that only happens when the gas is pristine and hasn't been disturbed by what we call feedback from surrounding stars or quasars. And so the parameter in our theory here is the so-called feedback distance or isolation distance that this seed needs to be. Basically, it's the first thing to form in its local patch of the universe. Now we can vary that parameter, and if we make that parameter quite small, so the patches are quite small, then we get lots of black holes. If we make that parameter large, we basically only occasionally get black holes. And we then can adjust this parameter, and we've explored different values for it. And for quite a reasonable parameter value, which is about 300,000 light years, is the distance we need, then we form just the right number of black holes to explain all of them that we see today in the universe. Yeah. So this model is basically, this theoretical model is trying to explain with a single mechanism all of the supermassive black holes. And then it goes ahead and makes predictions.
So at that point in time, Jonathan, the universe is dark matter dominated, right?
Well, it's most matter is still dark matter compared to the normal matter of hydrogen, helium, and all the other atoms today.
But compared to dark energy, it's more dark matter.
Yes. So then dark energy only fairly recently became a significant player in the universe. That's true.
So I'm just wondering, so if the supermassive black hole forms in this dark matter halos, presumably it's capturing a lot of the dark matter in the black hole as well, right?
That's right. So there's some dark matter in there as well. Now, these dark matter halos can be several hundred light years across. These small early ones, they become massive enough, about 1 million times the mass of the sun. These are the kind of dark matter halos that we think form the first stars. They need to be this massive to allow gas to be able to, when it falls in, to basically shock and excite hydrogen and cool, and then settle into the center of the halo. If the gas cannot cool, then it won't be able to settle and flow into the very center. So there are probably much smaller mass dark matter halos, so 100,000, 10,000, 1,000 solar masses, but they don't have strong enough gravity to create the velocities and the shocks needed for the gas to then cool. So only once the dark matter halos reach about 1 million solar masses, then the hydrogen helium gas that comes out of the Big Bang is able to cool and settle. Now it's cooling quite slowly. It's actually quite near equilibrium. It settles and it flows gradually into the center of the dark matter halo, and within about a few light years in the very center of the halo, then in fact the hydrogen helium is so concentrated it now begins to be a dominant over the dark matter locally. So there's more mass in the normal hydrogen helium than in the dark matter, and then it concentrates further and forms then we think the first star. And so it would be the mass. You see, in this 1 million solar mass dark matter halos, there happens to be about 100,000 or a few 100,000 solar masses of hydrogen helium. That's the ratio of normal matter to dark matter. So you see there's a natural scale here that can make these supermassive black holes if you can gather all this hydrogen helium that was in the dark matter halo and allow it to flow into the center. So this star, this supermassive star, will probably gain most of its mass from the hydrogen helium that flows in, because the dark matter itself cannot concentrate. It's weakly interacting, so it cannot concentrate so easily. So most mass for the initial seed will in this model come from the hydrogen helium, form a supermassive star, collapse to form a black hole. But now later that black hole can gather more hydrogen helium. Some dark matter will flow in there, but probably most of its mass gain will come from normal gas that's flowing in. Now, the reason I can speak with sort of some confidence about some of these processes that it's been simulated by many different research groups using supercomputers, taking initial conditions that come to us that we see from the cosmic microwave background, and we follow structure formation in the cold dark matter paradigm of structure formation, and they follow actually the chemistry of the gas as well, the hydrogen, helium, and follow the cooling. So there's actually quite a consensus on how this process leads to the first stars. What is less certain is this role of dark matter, and if it can actually change the structure of stars and allow supermassive stars and then supermassive black holes to form.
Yeah, so would it be correct in assuming, Jonathan, that the special conditions that existed a few 100 million years after Big Bang that produced the supermassive black holes, the quasars that we see, those conditions don't exist anymore, and hence there cannot be any more supermassive black holes being formed in the universe?
Exactly. So this is another attractive feature of this theory, to me at least. It's invoking very special conditions that only occurred in these first halos. Only there do we have the co-location of the dark matter peak the center of the dark matter halo with a single star. Later on, I mean, we're in dark matter halo now in our galaxy, but stars are forming in this disk of gas that's settled down, and this disk of gas is orbiting around at hundreds of kilometers a second. So the gas now, the motions of the gas is quite decoupled from the motions of the dark matter. And so you never have this co-location. So you cannot have this route of stellar evolution being influenced by the dark matter annihilation. Only in these first dark matter halos, where the gas is gradually cooling and settling in to the center, only there do you have these conditions. And that could naturally explain then why there's a very different mass scale. You see, other models, other theories for supermassive black hole formation would tend to start from lower mass objects, perhaps building up from clusters of stars, or gas clouds at first form 10,000 solar mass black holes. So they should predict many of these intermediate mass black holes, and only a few of them grow to become the most massive objects. But as we mentioned, we're not seeing, we haven't found many, if any, intermediate mass black holes. And there seems to be this natural separation of scales, which argues, I think, for quite a different mechanism requiring special conditions.
Yeah, I know that the physics is not clear even for the black holes in general, but do you anticipate the physics to be different for, sort of a small black hole and the supermassive black hole? Because the formation mechanism itself appears really different.
Well, if the physics of general relativity, those equations to describe the properties of these black holes in the same way. So you can have black holes of any mass, really. It's just whether nature can make them. And so what we're proposing here is that there are two routes. We're proposing a route through normal stars. So the most massive stars that form today around us, say 100 times the mass of the sun, these can make black holes with masses around 100 times the mass of the sun. And then we're proposing another route here through using dark matter annihilation to change the stellar evolution and allow supermassive stars to form and then form supermassive black holes. Yeah. But in principle, one could imagine black holes of different masses, from very, very low mass to even more massive. So it's just what nature can make.
Yeah, I was just wondering, even things like Hawking radiation and things like that would be different for the super.
Well, the microphysical process of Hawking radiation would probably be the same. It's just that the rate of this Hawking radiation is much faster when you have a very small black hole that has higher curvature. And so for very low mass, very small black holes, in fact, they are predicted to evaporate and destroy themselves by Hawking radiation very quickly. So that places one constraint. But these black holes, the mass of the sun, or 10 times the mass of the sun, or a million times the mass of the sun, that they have very, very low rates of energy loss through Hawking radiation.
Right. So they will be here as the universe.
Yes, they'll be here long after us.
So we'll take a quick break, Jonathan. When we come back, we'll talk about your paper on planet formation.
Thanks, Gill. See you in a minute.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we're back. Jonathan, we were talking about some very interesting research you're involved in, and that is creating perhaps a different mechanism for the formation of supermassive black holes, the very large black holes at the center of galaxies that might have formed very, very early in the evolution of the universe. You have another paper, 2014, Inside Out Planet Formation. You say the compact multi-transitioning planet systems discovered by Kepler challenge planet formation theories. So What is sort of the accepted planet formation theory today, and why did Kepler data sort of challenge that?
Right, so in the last 10 years, there's really been a revolution in studies of exoplanets, and part of that has been driven by the results of NASA's Kepler mission, which was observing hundreds of thousands of stars in our own galaxy and looking for very faint dips in light, we call them transits, as the planet passes in front of its host star. And because of its sensitive space photometry, it could very accurately measure the light from these stars, and thus was very sensitive to quite small planets passing in front of the star. And so the main result from this Kepler mission was it found many such transiting planets, and also many planets in multi-transiting, multi-planet systems that transit. So we call these the super-Earths, or Earth super-Earth sizes. That in this process, you measure the size of the planet relative to the size of the star. Basically, what fraction of the light is obscured by the planet. It tells you the size of the planet compared to the disk of the host star. So Kepler was sensitive to be able to see basically down to about Earth-size planets, and found this really unexpected population of so-called super-Earths. They're now thought to be very common. So it could be roughly that half of all stars like our sun have systems of super-Earth planets which are orbiting very close to the star. So far within inside the orbit of Mercury as compared to in our solar system, you would have perhaps 3 or 4 or 5, even 6 planets all orbiting around within the orbit of Mercury. So it's an amazing thing. How do we form these super-Earths so close to the star? I'd say the standard idea, the standard theory in planet formation is that these planets formed in the outer parts, much further away, the outer parts of the disk of material swirling around the forming star. We call this a protoplanetary disk. So they might have formed at perhaps 5 times the Earth-Sun distance, we call an astronomical unit. That's roughly where Jupiter is in our solar system today. That's where we expect most of the material to be. So that's what the conventional theories of planet formation were, and still are, saying. They form in the outer part of the disk, and then they invoke a new process of migration. So when you have a planet in a disk, it actually raises spiral arms in the surrounding gas. And there's an exchange of angular momentum with these spiral arms. We say there's a torque applied on the planet, so it actually spirals in, is the prediction. And then you could have a chain of migrating planets all sort of coming in. But, there's a number of problems, I would say, with that idea. One is what stops the migration. So why don't they just keep going in all the way to the star and get swallowed by the star? The other problem is that in such we call tidal migration models, you expect the planets to become locked in what are known as resonances. So we call them low-order mean motion resonances, where, for example, one planet will go orbit around 2 times around the host star, and a planet just inside will orbit 3 times. And that's known as a 3-to-2 mean motion resonance. And we know, in fact, from the Kepler data, we can measure the ratio of these orbital periods, how often they're transiting. So we actually can see if they're in these mean motion resonances. And most of the systems are actually not. So a prediction of these tidal migration models was not seen. So that's the standard view, though, and people are working to keep that theory going, and it's possible that it can apply. But what we proposed in 2014 in Inside Our Planet Formation is quite a different idea, and that is to actually bring in the dust and the pebbles from which planets are formed, bring that all the way into these locations at about far inside the orbit of Mercury, bring in the dust and pebbles into a sequential series of rings, which then form the planets, what we say in situ, in these very inner locations, at very extreme conditions. Typically around 1,000 degrees Kelvin is the expected location, the temperature of location where these planets would form. And that's the idea then, a sequential series of planet formation from the inside out, starting from pebble-rich rings that are trapped at a particular location. And that location we identify as a boundary between what's known as a dead zone region in the disk and a magnetically active region in the very inner disk. And it predicts then that this boundary would be at about 1,000 degrees Kelvin. That's the temperature you need to ionize sodium and potassium that's in the material to give you enough ionization to allow magnetic fields to couple to the disk. And that happens in the inner region. These magnetic fields allow angular momentum to be transferred very efficiently in this inner region. That clears out the inner disk and then leaves a feature in the disk at this dead zone inner boundary, which is, we think, a place where pebbles could be naturally trapped, and is a site then for planet formation.
You need a lot of pebbles, though, Jonathan.
Oh yes, so we need all the pebbles we can get. So we need all the dust to be accumulating into pebbles, and that's and then delivered into the inner region. So these are quite standard, I would say, theories and models for this. So we know interstellar space has dust. So remember, hydrogen and helium make up the bulk of the material. The heavy elements, carbon, oxygen, iron, and so forth, are about 2% of the mass of the normal atoms. And then about half of these heavy elements are in refractory material called dust, interstellar dust. So these dust grains then, in the dense clouds where stars are forming, can grow. They can coagulate and stick together. Also, ice can settle on the dust grains and help that process in cold conditions. And so, this grain growth is observed in protoplanetary disks. And the typical interstellar dust grain may be only 1 micron across, 1/1,000,000th of a meter. But we think there's evidence directly observed that they're growing to sort of millimeter sizes. And then once you reach these millimeter sizes, then they begin to feel sort of pressure forces and drag forces more strongly, which actually predict that these pebbles will spiral in to the centers close to where the star is. And in fact, that's a major problem in the standard theory of planet formation. How do you stop that process happening to build up planetesimals, things like equivalent to comets we see in our solar system today? How does that process happen if all these pebbles that you want to use are actually drifting in so rapidly?
So if I understand this correctly, Jonathan, so pre-Kepler data, the idea was planets form outside and they sort of migrate inward. And in this idea, it's really the raw materials going in and then assembling the planet pretty close to the star.
Yes, that's the dichotomy, I would say here. There's classes of planet formation which invoke planet formation in the outer disk, and then interaction of the planets with the disk to migrate the planets in. Or what we're proposing, and there's several other groups who are proposing these in situ theories where you actually bring in the dust and the pebbles to these particular locations and form the planets there. So
the Kepler data, does it indicate that the solar system is sort of special in this context?
All right, that's a big question. How common is something like the solar system? Kepler data measuring these transits is really sensitive to planets that are close to the star. It's not really able to see how common the things like our solar system are. Now, that said, having worked out the statistics of these transiting systems, because of course you only see the transits if the orbits happen to line up quite precisely, so there's a big correction factor. But once you have made that correction factor, you can estimate how common are these systems with close-in super-Earths, and they're very common. That's what's also amazing. So, as I said earlier, maybe 50% of all low-mass stars have these kinds of systems. So these could be the most common kind of planets out there in the universe. And actually, because most stars are of lower mass than the sun, about half the solar mass, and also of lower luminosity, at these locations, which are inside the orbit of Mercury, typically, the conditions are actually quite favorable for life. So you can have temperatures where water would be a liquid. So these systems are not only perhaps the most common kind of habitable planet, but most common kind of planet, but also the most common kind of habitable planet and habitable environment. So they're extremely important to understand. And yes, our solar system then is quite different, and one would then want to know why that is, and that's an active area of research.
Yeah, since the super Earths are close to the star, they won't be, right? Would they?
Sorry, can you repeat?
Yeah, the super Earths, very close to the host star. They won't have water, right? Well, it'd be too hot, wouldn't it?
So most stars are of lower mass than our sun, and
Yeah.
the luminosity of a star depends actually very strongly on its mass. So for many systems, in fact, this so-called habitable zone is much closer in where the Earth is relative to the sun. It could be perhaps 10% of the distance or 20, 30% of the distance. So many of these super Earth systems actually have planets in this so-called habitable zone. And again, not our group, but other researchers have sort of crunched the numbers and done the statistics. And given the demographics of these Kepler-type systems that have been found, they estimate that perhaps one in 10 stars like the sun have not only these super Earths, but a super Earth in the habitable zone. So these habitable environments now are thought to be very common in the galaxy. And if there's 100 billion stars in the galaxy, then if 10% of them have habitable zones on rocky-like planets, that would be 10 billion habitable worlds in our galaxy, which is an amazing thought.
Yeah, but the Fermi paradox still exists. We haven't seen anybody.
Right. So, in fact, you asked the question: do they have water? So, many of them are at the right temperature to have liquid water, but it's a separate question of whether water, or significant quantities of water, is delivered and captured by these planets in these locations. And that's again something we and other groups are working on. So, can we follow the chemistry of the gas, the astrochemistry of the material delivered, and will water be delivered to these potentially habitable worlds, should we say?
Yeah, so like I said, the size of the star and the luminosity really drives a habitable zone. So how much does the sun have to shrink before Mercury becomes a vacation spot?
Right, so we could basically work out the equilibrium temperature. So Venus is just a little bit too far in. Venus is at about 0.7 astronomical units, and Mercury's much further in at about 0.4. The energy we receive depends on the inverse square of the distance. And so you would really need the sun to reduce in luminosity by quite a large factor. And of course, the actual evolution of the sun is to go in the other direction. So gradually the sun is becoming more luminous over time, slowly over billions of years. And so and then at the end of its main sequence life, when it becomes a red giant, of course, will become hundreds and thousands of times more luminous. And so actually we'll be going in the opposite direction at that point.
Yeah. So, we have a lot of Kepler data. There's other data coming in. What is the general consensus about habitability and life outside the solar system? I mean, generally people say it should be abundant, but we have no evidence for it. Have we moved away from that idea that the universe should be teeming with life to something more of a moderate expectation, or we are still at the initial point?
Well, the outcome of this work in exoplanets is really moving in the direction that habitable planets are very common in the galaxy. So as we mentioned, there could be 10 billion habitable worlds in just our own galaxy. And so this data, this is based on real observations of exoplanet systems. So that is a real revolution. It is still then a mystery as to how common life can get going. Do we have the right chemicals delivered to these planets? Perhaps if you're too close to your host star, you may be adversely affected by flares from the star, potentially X-ray flares or other stellar flares. And so perhaps that has to be accounted for. Or it could be more to do with how often intelligent life, multicellular life, and intelligent life evolves. We don't have many examples from which to draw. So all we know in the case of the Earth is that simple life got going very quickly, basically as soon as it could. but it did take several billion years for multicellular life to arise.
Do we need a more stringent definition for habitability, or perhaps even more stringent definition for really life evolving conditions?
I would say that as long as we're careful with our definitions, then then we can talk in terms of habitability, in terms of the temperature constraints that are needed. And most astrobiologists would say we want to be in an environment where water would be a liquid. And then one could talk about chemical habitability, that we need to have the right compounds delivered to the planetary environments. There's perhaps less consensus on exactly that chemical habitability definition. Yet other astronomers talk about regions of galactic zone habitability. If you're in the center of the galaxy, perhaps too close to a supermassive black hole, or where we know the cosmic ray fluxes are very high, then maybe that could have an effect. But you could always have life in underground or deep in an ocean, shielded from such effects, I suppose. So there, it's less clear if one could make a simple boundary. So I think that the definitions of temperature as a starting point are good. It's a necessary condition, we think, to be in this habitable zone in terms of temperature, but not sufficient. So we do need also to have the right chemicals. We need to have water actually present on the planet, and then probably many other compounds are needed as well for life. What's really interesting these days is that the most powerful telescopes now in the radio regime are able to find these compounds. So we're actually seeing prebiotic chemicals in space, and they seem to be quite common. And so this is another piece of information that argues that perhaps from the chemical side, it's not such a limiting factor.
Yeah, plenty of habitable planets, plenty of raw materials, but we still can't find anything. So I want to finish up, Jonathan, by going back to the supermassive black holes. I know that you're doing a lot of work in this area. So if you look forward 5 years, where do you think we will make sort of the biggest leaps in this area, both in terms of formation, but also it is now intimately connected with the question of dark matter? Where do you perceive that we will have the biggest contribution?
That's a great question. So there are many things potentially able to be happening in the next few years. So we obviously await the launch of the James Webb Space Telescope, which will really have the ability to see into the very distant universe. Now it's not got a very large field of view, so it's not going to be able to survey large regions of the sky. So if these objects are very rare, then it will struggle perhaps to find them. But our particular theory is predicting actually to be quite common at these early times. And so within any particular field of view of the James Webb Telescope, in fact, we should see high redshift quasars. But the question is whether they will happen to be feeding from gas that's falling into them. So those James Webb Space Telescope observations are really what I'm looking forward to. But if the particle physicists find the dark matter, of course, this is very, very important for this theory and many other works in astrophysics these days. And we do need it to have certain properties. So we will pay attention to what is found there as well.
Yeah, we have ruled out the idea that primordial black holes could be a candidate for dark matter, right? That has been ruled out.
Well, only in certain ranges of mass. So, as we mentioned, black holes can, in principle, have a wide range of masses. It's just how does nature make them? We mentioned routes through normal stellar evolution to form black holes a few times the mass of the sun, maybe up to 10 or 100 times the mass of the sun. And we mentioned supermassive black holes, which may form in a different mechanism. Maybe in the very early universe, there were ways to form black holes of quite different masses. And these are what are then referred to as the primordial black holes. They would have existed before the very first stars and galaxies. Yeah. And there's still a range of masses that are untested. certain ranges have been ruled out from microlensing searches in our own galaxy because if black holes, if they existed, would cause gravitational lensing events to be seen. They're not seen at the rates predicted. But there's still a range of masses that are in play, and it remains a possibility.
Can you handicap Planet 9 being a black hole?
Well, first I need to be completely convinced Planet 9 is there. But then if it is there, I would be very, very doubtful that it's a black hole. Because, as I say, there's little, we don't know of astrophysical mechanisms to make such small, low-mass black holes yet. If it's true, it'd be extremely exciting. Then we need a new theory, something else to work on.
Yeah, we will be solve an energy problem too.
Yes, send some material into the black hole. That would be an interesting way to solve the energy problem.
Excellent. Yeah, this has been great, Jonathan. Thanks so much for spending time with me.
Thank you very much, Gill.
Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.